All right, so what we're looking at today, and this is your Calc 30L, the extension of Calc 30 here, as derivatives of inverse functions. So we've talked about derivatives of inverse trig functions last day, right? Like arc sine, arc cos, and that sort of thing, what those derivatives are and why. So we did that in the last couple lessons. What we're going to do today is find out how do we determine the derivatives of inverse functions that aren't trig functions. And there's actually a bit of a different way we want to do that. So how I want to lay this out is I want to set, okay, so I'm going to set g of x. I'm going to let that equal to the derivative of f of x. No, I'm not. The inverse of f of x. F to the negative 1 of x. Now, if we were going to graph that, let's say we have a function like this. We have a parabola. Okay. Now the inverse, if you recall, the inverse still means reverse. And what do we reverse? We reverse xy. So xy becomes yx. Everyone remember that? And what that ends up looking like is a reflection about the line y equals x. And so this point would go over here. This point would go over here. This point over here, and this point way over here. So what we'd end up having is we'd have this parabola would turn into a parabola that kind of goes sideways like that, right? It's reflected about that line. All right. So this now is g of x. Got it? That's g of x. So one of the properties of inverses is that when you multiply them, or in this case, when we're talking about functions, when you compose functions, and you remember what composition of functions are, like f of g of x, that's a composition function. When you do that, you get something special. Does anyone remember what can anyone figure out what we might get if we do this? They're inverses of each other. So, sorry? It is. Yeah, it's x. So if you have this g of x is the inverse, it's like f of f to the negative 1 of x. So f to the negative 1 of x, right, if you put that inside of f, you get out x. So this is what we get when we compose these two functions. So in order to look at the derivative, let's just look at what happens if I literally differentiate, okay, this side, and differentiate this side. So it's kind of like implicit differentiation with the chain rule. Okay, we're going to differentiate both sides. So this is what it's going to look like. We're going to have the derivative of f of g of x, and the chain rule says I have to then multiply by the derivative of g of x, and I'm using Leibniz notation here, obviously. And the other side equals 1. Right? I'm going to change the notation because all of this d over dx is going to get a little bit complicated here. So I'm going to change this. I'm going to write this now as f prime of g of x times g prime of x equals 1. Okay, so if we look back to the title, I want the derivative of the inverse function. And that's this. G of x is the inverse function, and this is my derivative. So if I solve for this now, I get, over here, I get g prime of x equals 1 over f prime of g of x. And if I substitute back in, if we want everything in terms of f of x, then this is what this looks like. And I'm going to go back to Leibniz notation because this is what you'll see in your textbooks a lot. This right here is actually the derivative of f to the negative 1 of x, isn't it? That's the derivative of the inverse function of f of x. And this equals 1 over d dx of f to the negative 1 of x. So I'm just going to let that sink in for a minute, okay? Because I know you're thinking, oh my goodness, what have I gotten myself into today? Well, it's not that bad. And this is actually going to be very, very helpful for us. Because remember, in calculus, some things look tough, but they aren't. And then other things don't look tough, but they are, right? This is one of those things that looks tough, looks complicated, but it's actually going to help us to determine values, like actual slopes of tangent lines to inverse functions. And the big thing is, without us having to clearly define what the inverse function is. So we don't have to explicitly express f to the negative 1 of x. We don't have to actually find that function in order to find its derivative at a point. And now you're thinking, that was supposed to make things easier? That made things worse for me. Anyways, let me explain a little bit more. Okay, so we move down here. Okay, I just want to show you this. Now, don't copy this down just for now, okay? There is a theorem that I'm going to try to explain, and I'm also going to just show you this graph here a little bit. So I'm going to try and keep this simple and straightforward, okay? I know sometimes I can talk myself into circles too, so I'm going to try and keep it straightforward. So this theorem, first of all, this theorem says derivatives of inverse functions. Okay, if f, now this is f of x right here, this black line right here, if f is differentiable at every point on an interval I, so let's say that, like an interval I, from here to here, whatever, right? Or really anywhere. This is all of x, it's differentiable really. So if it's differentiable and the derivative of f with respect to x is never 0, so you never have a local min or a point where the derivative is 0, as would be in this like exponential function or something, right? If this was an exponential, then f has an inverse f to the negative 1 that is differentiable at every point on the same interval. So if it's never 0, and if there's no cusps or corners or big gaps or anything like that, then we know that there's always a derivative on this. So that's a bit of a caveat there when we talk about, this formula, right, or this definition, because this only exists under certain conditions, and that's the case with a lot of things in calculus, right? Sometimes things don't exist at certain places. So that's just a little bit of caveat. Okay, now this part, I don't know if this is going to help or not, but let's say we have this part right here, x, y, okay? And I want to find out, the derivative on the inverse function, because right now this is the inverse function, right? I want to find out what this derivative is right here. But I don't want to clearly define what this black line is, what this f to the negative 1 of x is. I don't want to have to find that, because that's going to be too tough. So you could obviously switch x and y, right? Solve for y, whatever, blah, and take the derivative of that new function. Fine. But what happens if it's a really complicated function and you don't really want to solve for y? You can't solve for y. Like, it's just too tricky, right? So this is going to help us that way. So I want to find this, but what I want you to notice is that, and this is a poorly drawn diagram, I understand, but this tangent line right here and this one, they're connected. Okay, and the reason why they're connected is this y value is now this y value over here. See, that kind of like turns into the x value, right? Because it's reversed. And this x value is really now the y value for this function. Okay, so x and y are reversed. So really, this right here, this slope of this line is the derivative of the inverse function at a certain value x. Now, this x really is the y to the original function. Okay, so if this was x, this would be f of x for this. But this isn't x, this is actually y. So when you put y into right here, you have f of y. And f of y is really what the inverse is. Okay, so this is like the derivative of f of y. So here's a function, and there's the y value from the original one. So I'm not suggesting that we talk in terms of f of y, but maybe when we do our next set of questions, we're going to see why this is y. We'll see why this is. Okay. So one last thing I wanted to show you is that this slope, okay, and this slope are really inverses of each other. Okay? So if this was like a positive 3 over 2, this would be a positive 2 over 3. They're 1 over. We have to account for these functions being different, but really we have the slope here of the tangent line on our f of x, okay, is 1 over, and this really would be the f of x function, I guess, right? And this is the f to the negative 1 of x. So they're reciprocals of each other. And if I just do a rough sketch here, like this one here is pretty small, right? This one here would be pretty large at a mirrored point. Okay? So they're reciprocals of each other. So that's important to think about that. So these derivatives that we're comparing now are reciprocals. Okay. All right, so what we're going to do here, and I did include the link here. Let's make that a little bit smaller. It doesn't have to be that big. I did include the link, and this is on your Google Classroom. And it's archives.math.utk.edu. And we can look this up, and you can look up the worked out solutions here for each of these. But what we're going to do is we're going to find, and you can write this down. This is going to be your kind of examples / practice for yourself. So we're going to find the derivative, and there's different ways you could write that, okay? And this is one way. Looks a little strange, but the derivative of the inverse function at the given point on f to the negative 1x. And so here would be the function f of x, and here would be the point. And we're gonna go through a few of these together, anyways. All right. Oh, I worked all these out and had like an answer key, but it's at home. Huh. There we go. That's what I get for doing calculus on the weekends. It doesn't pay. I mean, if you're a student, you have to, but not as a teacher. Why would I do that? I just leave my stuff at home. Okay. So anyway, so see if I can remember what I did. All right. So when we, again, with our newfound friend here, this little formula, this little definition right here, we're going to be able to find the derivative of the inverse function. And all we have to do, guys, the big thing we have to do is find the derivative of the original function. So if we're given f of x, we find the derivative of f of x first. So let's go back to the other page. I mean, maybe some steps would be appropriate. Some steps, okay? 1, find f prime of x. That's step number 1. So if we're doing question number 1 here, I would say, okay, f prime of x, it's pretty easy. That's 3x squared plus 7. Okay. That's the first thing you do. That's super easy. For all these, pretty easy. Not too bad. Pretty easy. Okay, so let's go back to our friend again. And what else do I need? Okay, well, I need now to put a value into this derivative. Okay? And remember we said that this is like f of y. It's not f of x, it's f of y. Okay, well, let's see if we can figure that out here. So this is a point on the what? The inverse function. So this is like x and this is y for the original function. Okay? Now, if we're talking now about if we're talking about this function, the inverse, then, oh gosh, what did I do? Okay, then, so this is now yx, it's not xy, it's yx for the inverse function. But this is going to be my input variable, y. If we call it y, then this is going to be f of y. You see, instead of on the original function it would be 110. So that's x and f of x. This is now on the inverse function. So this is my original y, and this is f of y. So all this to say, and that's super small, sorry, you probably can't even see that. All this to say is that if you're given a point on the inverse function, you use the y value here, the second value. And that's going to be That's going to be f of y. See, that's going to be this value. And so, especially when you're given a point, it's super easy. So, step 2, I should be on step 2 here. Plug, and I'm going to put y value just in quotes because it's really the f of y value. Plug the y value for f to the negative 1 of x into definition. And so, again, that definition, we'll just rewrite that again. So d of dx of f to the negative 1 of x is 1 over d dx f of f to the negative 1 of x. So I'm sorry, but you're just going to have to memorize this ugly thing. But the derivative of, see, and the neat thing is we can skip right to the derivative of the inverse. And that's going to be evaluated at 1. See, this is the value of 1 that I need. Okay? So it's going to be 1 over, what's the derivative of f of x? Right here. So 3, right? 3x squared plus 7. But what do I put in here? Again, I put in 1. So the derivative of the inverse, d over dx f to the negative 1, yeah, I guess evaluated at 1. It's 1 over, so this is 3 plus 7, 10. 3 plus 10. 1 over 10. Okay? Now, without all the detailed explanation going back and forth, let's do another one. So let's do this one right here. I'll just clip this and bring her down a bit for us. Okay. All right. So, if we're going to find the derivative of the inverse, evaluated at 13, 1, that's a point of tangency, I find, first of all, the derivative. And now, the d over dx of f to the negative 1 of x is going to be equal to 1 over this derivative with f of y, or this 1 value, plugged in. That's it. Okay. All right. Okay, so if we look at this on Desmos, okay, the red graph here is y equals x cubed plus 7x plus 2, and that's our number 1 question there. Okay? So what we're trying to find out is if we had the inverse graph, what would be the slope of the tangent line on point 10, 1? And this is what we've calculated it to be, about 1/10. So if we're checking the reasonability of this, what we'd want to do is we'd want to create the inverse graph. So I just reversed x and y, came up with this graph. And does that look like it's a reflection of y equals x? Sure does. Look at that. It's a complete reflection. So at the point 10, 1, okay, it looks like we would have a, where's 10, 1? 10, 1. Looks like we would have a tangent line that does have a slope that's pretty close to 1 over 10. Okay? Now, I'm pretty sure there's a way on Desmos here to find the tangent, just to do a tangent. Anyone know how to do that? I didn't think so. You guys are no help at all. So what we're going to do is I'm going to just create a line, 0.1x. And what I'm going to do, oh boy, it's going to be tough actually. What I'm going to do is, can I just see if there's more than one? Oh. So 0.1x All right, watch this. This is going to be super cool for you guys to see. Actually not, but so this is going to be, let's go from 8 to 12. Okay, and let's go y values from, what was y value like, so 0.2 to 3. Okay, that's a little bit better. You kind of see how this is looking like a tangent line. So I don't know. Do I have to move that up a bit or what? Plus what? 0.01. Oh, there's no intersection point there now. I think we might have been. I guess we could figure out what the equation of the tangent line is, right? But that's not the point. The point is just to see if this is reasonable. Does that look like it's pretty close to a tangent line right there? Like I think that might be, that's pretty close there, isn't it? See, I'm on this. Look at that. That's beautiful. So, did we do that right? It appears that we might have. Good for us. We accidentally might have done this right. What about this one? Do we even dare? I don't know. Do we dare plug this in and plug the inverse in just to see if this is right? No? Okay. I didn't want to do it anyways. You're right. Let's not do it. Okay. So instead, I'll get you guys to do some work then. Ha You should have said yes. Okay. So I want you to work on these right here. So you copy those down, leave yourself some space, get practicing sort of this definition of the derivative of an inverse function. See what you get. And then I will encourage you to take one of these functions, and I want you to, on the graphing calculator it might be a bit tough. But perhaps on a computer, Chromebook or whatever you have there. If you have one, you can get onto Desmos. You can grab your phone if you want. And do what I did. Plug in the inverse. And then find out if your slope matches with that point of tangency for that inverse function. Okay? So I'll just show you some solutions here just as I go here. So for question number 3, the solution would look like this. Now again, I just asked you to find the value of the derivative. I think the original question asked you to find the equation of the tangent line, but that would be your answer there, -1/2 for this one. Over here would be 1/9 for number 4. Okay. Number 5 would be this right here, which simplified I think also is 3/11e, something like that. And this one here is maybe a little bit more involved. Turns out just to be 1/3 though. That's for this question right here. And these would be some extra credit bonus sort of for you. I'm not going to give you extra credit, but the extra credit for you. Just to say you did it. So here's what these ones look like. So right here it'd be 1/9. So it'd be 1/8. Now arctan was from last lesson. There's a definition for the derivative of arctan. It turns out to be 1/10. So the arctan squares, 1/1 plus x squared, I guess. And then there's the last question there too. 2 minutes later. So just to remember, this is your definition here of the derivative of an inverse function here. Right there.